Okay, so welcome to this CAM Colloquium. Thanks for tuning in. So I'm really pleased, actually. Pieter and I are good friends. So Pieter van den Berg and I met some time ago when he actually visited while he was a PhD student. And he spent just a few months here during a winter semester. So we're hoping to get him back sometime in the summer. So Pieter later joined as an assistant professor, transportation and logistics at the Rotterdam School of Management at Erasmus University. His research is in a bunch of different logistical areas, focused on emergency service providers, which is the link that we have, but also in public transportation. So he's actually also got another claim to fame. He's very recently, maybe, what is it, like 4 months ago now, Pieter, a new father?
Yes.
So, yeah.
But next week, 4 months, yeah.
Yeah, but surprisingly, he is actually getting some sleep these days, which is kind of cool. So Pieter, welcome, and maybe I'll hand it over to you in just one sec, just two more announcements. We are recording the talk, so please keep that in mind. Please stay on mute and keep your camera on if you can. That's always kind of fun. Okay, sorry, Pieter.
Yeah, thank you, Shane. Yeah. So I'm very pleased to be here and to basically get some memories from me visiting Cornell. I digged up some pictures and I think this one, the one on the left is much more representative than the one on the right. I think that one I took on the last day before I left. And I think that was the first day that there was no snow on campus. So I think the one on the left is much more representative of the kind of weather that I've seen at Cornell, and I would certainly like to be back at some point. But for now, I'm happy to be back virtually. So that's all really good. I will be talking about some work that I've done with mainly a PhD student of mine, Ayman Abdelwahid, and some other co-authors that we did in a project on electrifying transit bus networks, and I will introduce that directly. I have like a couple of topics in the talk. So most of the work will be about developing charging schedules for these bus companies. So when and where should a bus charge? But I will also spend a bit of time on real-time re-optimization. So what happens if a bus runs into some problems like delays and misses the charging? What happens then? And I hope to have time to also discuss a bit about what if a bus company would have their own renewable energy, and can you use that to charge the buses, and how can you align the renewable energy generation and the actual charging of the buses. So that's a bit of the outline. So how did this research start? It was actually nicely aligned with me starting here in Rotterdam. Because in 2016, that's the year that I started here, there was an agreement between the Dutch government and all public transport operators in the Netherlands. And there they promised that they would, by the year 2025, all new transit buses would be fully zero emission. And ideally by 2030, they would actually replace all the diesel buses by electric buses or other types of zero emission buses. This leaves like only about 10 years for the public transport operators to make some massive changes to their operations. And we were involved in this process from 2017 onwards. So within my school, we joined a big European project sponsored by the European Union to basically support this transition to electric buses. And we started working with them in 2017. And only 2 years later, they actually started operating their first electric buses. So that was by the end of 2019. So they're operating for a bit more than a year now with at least 50 electric buses. And they are planning to have more and more very soon. Yeah, thank you, Shane. Indeed, if you have any questions, feel free to interrupt me or use the chat because I do have an eye on the chat. So try to respond quickly, but I'm also fine by you just interrupting me and asking your question. Okay, so if you decide to move away from a conventional diesel bus, which all the Dutch public transport operators had to do, then there are multiple alternatives, and basically all of them like involve some sort of electric buses, which are emission-free, depending on where you get your energy from, but at least locally they are emission-free. They typically have much less maintenance and higher fuel efficiency, so that's some of the benefits. But that does at some point also come at a cost, especially an operational cost. There are different ways of operating electric buses. So you could have the one with a grid connection, so with these overhead wires, for example, or you can have some sort of generation on board. But the type of electric bus that we are looking at is a battery electric bus. So that's a battery that, a bus that has a battery on board that is used to power the bus. And some of the downsides of these types of buses is that they have a rather low energy density. It takes quite long to charge these buses. And if you do the charging, especially if you do fast charging, then the impact on the grid is also quite significantly. So it actually requires a lot of energy to charge like a fully electric fleet of buses. But the operational aspect that we will be mainly looking at is the combination of the low energy density and the long charging duration, because this really makes it operationally much more complicated, because you need to charge the buses during the day, and that also takes much longer than just fueling a diesel bus. So you actually need to change your operations to accommodate this charging. Question that I often get is, why don't we just swap the batteries? This definitely is an option. So there are systems with electric buses where instead of charging the buses, they would replace the batteries during the day. The public transport operator in Rotterdam did not choose for this option. I think there are a couple of different reasons for that. Mainly that for this swapping, you typically need some infrastructure, which also means that, which you typically do in a central location. And that would also mean that buses during the day need to go to the central location to swap their batteries. And they found that operationally quite complex. So they decided to go for fast charging, where you basically connect the charger to the bus, for example, at the terminal station, and then quite quickly try to charge the battery. Depending on the power and the size of the battery, this can take like maybe from an hour or even more to actually fully charge your bus. That's like roughly the number that you should think of. So once we know that we want to use this battery electric buses, and we want to do that while using fast chargers, then there are quite a few decisions that still need to be made. I classify them here like more strategic questions, like what types of chargers do I use? How many chargers do I use? What will be the locations of these chargers? What types of buses do we use? So there are a lot of more strategic questions. Then on a tactical aspect, we have like the scheduling. So which bus should do which trip? And how many buses do we use in the actual operation? And then we have more operationally, and that's the question that we will mainly focus on, is the charging strategy. So that is, which bus should charge at what time, at what location, and for how long. So in most of the work that I will be talking about today, we focus on this particular problem. So we take the schedule as a given. So we have a schedule, and we take that and try to include charging moments in that schedule without delaying the buses. So really use the layovers that the buses have to charge the buses. And then the question here is, when should which bus charge at what location? Okay, then maybe something about the city that we work with. So this is my home city now for a couple of years already. This is the city of Rotterdam. And as you can see, it's nicely split by the Maas River. So this is the river that runs through the city center. And this also to some extent divides the network, the network of this public transport operator. So they decided to first electrify the northern part of the city, so everything north of the river, and then later on electrify the south of the city. And that in itself might be interesting, but what for us was most interesting is that also the structure of the northern part of the city is quite different from the southern part of the city, from a public bus point of view. On the north end of the city, they have a lot of lines, and there is no real central station that is used where all the buses at some point stop. So that also requires that the charging is spread out much more over the city in the northern network. Whereas in the southern network, we have one central station, and all of the buses at least have one of their terminal stations at this location. So that also means that for the southern network, they have the opportunity to have all the fast charging at this particular location, and all the buses can charge there. For the northern part of the network, that is not possible because all these buses have different terminal stations. So there is more spread out charging in the northern part of the network. I will come back to this when discussing some of the results that we had. Okay, really early on in the project, so they just heard that they had to go to these electric buses quite quickly, and they had no idea what the impact would be on their operations. And that's the first thing that we did. So what we did is, what would be the impact on their operations if we would replace all the diesel buses by electric buses? And we did that by basically running a simulation model. And in fact, we started off with a simulation model without any uncertainty. So basically, we would do some sort of trace driven. We would see what would happen with the state of charge of all the buses in all kinds of different scenarios. And for that, we took as an input basically the bus assignment schedule. So that is the schedule that says which bus should operate which trip. Then another input was the number of chargers. So that gives you the availability of the chargers and the locations of these chargers. As an input, we had the charging power, the charging strategy. So when, where, and how would we use the chargers? And then the capacity of the buses, because at the time they did not yet buy the buses, so they did not yet know what the capacity of the buses was. And in this decision, they actually wanted to know, like, what is the impact of some more capacity in the batteries? How much easier would that make our life if we have a larger battery, for example? And also the energy consumption rate was something that they did not fully know, but at least we had some scenarios for that as well. And then their question was, to start off with, maybe all of this is really easy. So maybe it's just feasible to keep the diesel bus schedule that we have been operating for years and years. And if we just have enough chargers, so if at every location where we plan to install some chargers, what if we have a lot of chargers there? Would that be enough, given the layovers from the diesel bus schedule, to get like a feasible operation? So that was the first question that they had. So what we did, we basically did not look at the number of chargers. We just say we always have enough chargers. We don't really look at the strategy of charging, because if there are enough chargers, we just say charge the bus whenever you are at the charger and you have a layover. And then as a bus schedule, we use like the diesel bus schedule that they have been operating before. And then, of course, the question was, will this actually work out? Or how many of the buses will run into troubles if we don't fix this? So some of the results. So what we see here in these graphs is, so they had two scenarios for the energy consumption. So that is the amount of energy that a bus would use for each kilometer driven. And what we see here is different charging powers of the chargers and different battery capacities. And what you see in the graph is then the number of buses that at the end of the day would have a state of charge less than 10% somewhere during the day. In total, we had 74 buses in this network. And you see that in the basically worst case scenario. So with a high energy consumption, the lowest possible charging power, and the lowest possible battery capacity, you will see that I think 59 of the 74 buses would not actually be able to make it to the end of the day, because 10% is really like a lower limit that they want to use in planning. They actually want to use quite a bit higher, because there's of course a lot of things that can happen during the day, such as delays, higher energy consumption as a result of the weather. So there are many uncertainties that are not taken into account here. But even without all that uncertainty, you see that in this scenario, it would clearly not be feasible to just take this schedule and operate that with electric buses. But also, if you look at the more optimistic scenarios, so suppose you would go for the highest charging power and the biggest battery that was available in the market at the time, and take the lower energy consumption estimation that they had in mind, even then, at least some of the buses would have some troubles, in this case with no uncertainty. So for them, it was very, very clear from these results that they will have to adapt their schedule, because basically none of the configurations would yield a feasible schedule. And that is even ignoring all the uncertainties that they know they will have in their operations. So that, at least for them, was also a good reason to keep working with us. First of all, we showed them these insights that they didn't really have themselves, but also that we basically found out that more work needs to be done. And we were the ones actually doing some of that work. So that's basically in the next phase of this project, we decided that we would focus on the optimization of charging schedules, because they did not really have any software that could assist them in that. And they did have some software to make better schedules. So to get a schedule where at least you would have more layovers, so that you have more time for charging, so that hopefully you would get a feasible operations with your electric buses. But they also quickly realized that probably you need to do something smarter also in deciding when and where to charge. And that was the focus of our work mainly. So basically the problem description that we got from them was, can you come up with an optimized charging strategy? So where, when, and for how long should each bus charge during the day? And the objective that they gave us was to minimize the charging cost, or also maximize the grid integration. So as I said before, charging these electric buses, especially with these fast chargers, does have a very big impact on the energy grid as well. So it would not be wise to charge all the buses at the same time. So there's really this this factor that plays a role here as well. And especially since our project was also together with the municipality, and also the grid operator was involved, we think like it would be a good objective to basically charge whenever there is excess energy on the market, and maybe not charge the buses when there typically is a shortage of energy in the market. So for that, we will basically use the spot market on the energy market as a sort of indicator of how demand and supply matches in the energy market at that time. So what we did, we developed a mixed integer linear programming formulation. So we modeled this as a mixed integer linear program, where basically as an input, we would get a schedule from the public transport operator. So they would basically make changes to the schedule, give us the schedule. We would optimize the charging schedule and see whether it would be feasible. If not, we basically do multiple loops where they change the schedule and we do the calculation. So there was like a bit of a back and forward going on there. Other input was the network structure. So where are the lines, where are the bus stops, basically everything related to the network. Then for the objective, we had this energy price signal. So we basically use fluctuating energy prices to mimic like demand and supply on the market. These are not actually the prices that the bus operator pays. They have like other agreements with the grid operator, but still this is a nice indication for what the market situation is at a given time. And then we had a whole bunch of practical parameters, such as the setup time of a charger, the charging efficiency. A lot of practicalities also played a role, and we got them as an input to our modeling. Then on a high level, the optimization involved an objective to minimize this charging cost, or could also say maximizing the integration with the grid. So try to charge at good times. And then we had a bunch of constraints. So some of them related to the state of charge of the buses. So there is an upper limit and a lower limit. So the lower limit basically says in the scheduling, we never want to have a state of charge lower than, say, 30%. And an upper limit we also have, because we don't want to charge the buses over 90% during the day. Because I think it's a well-known fact that batteries charge much less efficiently if they are closer to fully charged. So for that reason, they decided to not charge above 90% during the day. During the night, they use a slow charger, and there they can actually use it till 100%. But during the day, using the fast charger, they have like a limit of 90% for that reason. There is a capacity on the charging. There are a lot of practicalities. The minimum amount of charging time, they don't want to plug in the charger for only 1 minute of charging. So there is a couple of practicalities there in the model, and we are able to model all of these that they had. And then as a result, we get an optimal charging strategy where basically for each bus, we know which of the stops at terminal stations should be used for charging. We actually had two different formulations of this problem. Both of them were almost equivalent. They were not exactly equivalent, and I will discuss the differences between the two. But the first thing that we tried was maybe a bit of a naive approach, where we would basically discretize time to the minute. And for each minute, we then decide if a bus is at a location with a charger, does it actually use the charger, yes or no? So it will be a binary decision variable that says, during this minute, should this bus be charging? And later we found out that most of the charging events start at the moment that either a bus arrives at the station or a bus departs the station. Even though this is not a requirement, it is possible to maybe that two buses arrive at the same time, one starts charging, and then after 10 minutes they swap places. That is in principle feasible. But we figured out that if we would limit ourselves to only start charging at the moment that either a bus enters the station or leaves the station, that could potentially speed up our modeling and is a bit more practical. So it's not a hard constraint that you can only do that in practice, but if no bus is arriving or departing from a station at that given time, then it's not always clear whether there's actually a driver that is able to move the bus away from the charger to make place for another one, because they might have the lunch break, or so there's a lot of other constraints for the drivers. So we cannot be 100% sure that there is someone available to actually move the bus if we swap the charging bus at the moment that there is no bus arriving or departing. So from a practical point of view, this formulation was actually also quite convenient. So if we then look at how good the formulations is, or what does it do for the objective. So the DTO, so this discrete time optimization, has the benefit that you have higher flexibility in changing the charging bus. So you could indeed, if you have a long charging slot with two buses present at the station, both of the buses could use half of the slot. And that is not possible in the discrete event optimization formulation that we have. But on the other hand, in the discrete event optimization, we are a bit more flexible in the charging duration. you could, this is a very minor technicality, but you could also charge for example, 4.5 minutes instead of 4. And in principle, that could give you like a bit of an edge compared to the discrete time formulation. But the most important reason is that the DEO is expected to be much better computationally, because you have a much smaller problem. Only when a bus arrives or departs, you have to make a decision, compared to every minute you make another decision, like which bus is charging. So we expect the DEO to be much faster and also to be much more practical. The resulting solution is much more practical. However, we do expect that the DTO gives a slightly better solution, purely looking at the objective. Okay. To illustrate that a bit further, to see what this means. So suppose here that we would have 3 buses, and one indicates that during this time slot, this bus is present at a given station. So in the discrete time optimization, you would basically be allowed to change the charging bus at any given time. So you can basically every minute decide, if there are 2 buses, which of the buses should be charging. Whereas in the discrete event of the optimization, we would only look at the arrivals and departures of the buses, and that would determine whether the moments at which we can make a decision. And you already, in this example, you see that you go from 12 decision moments to 6 decision moments. And so for a more practical, like real life case, the gain that you get is actually much, much more. So, and here, instead of only 0, 1, so it's not only that during such a time slot, you either charge the full time slot or only a part of the time, you can now also say, okay, I only charge for 3 minutes during this time slot. It does not mean that the other bus can take over the final minute. So for example, between time slot 4 and 8, we have 4 minutes, but we cannot say that bus 1 and bus 2 both use 2 of those minutes. So we really restrict us to only one bus that can use this particular time window. Okay, so this is how the input of the problem would look like then for the 2 different formulations. And what we will do, so we have this optimized schedule, and we compare that to 2 common sense strategies, as we call it. So we thought about, like, if you don't use any optimization technique, what could you do to still decide which bus you charge? And the first thing that came to mind is just a first in, first serve. Just whenever a bus comes at a station where there is a charger, and the charger is available, it will just use the charger. And if there is no charger available, it joins a queue, and maybe at some point the bus that is currently using the charger leaves, and then it could still use the charger. Important to note here, we never delay the bus for this. So passengers will not notice this charging. It's really, you only use the time that is there between trips anyway. So it's not that if the charger is full, if the charger is occupied, that you leave later because you still want to do some charging. We just assume that you only charge during the layover, and trips are not delayed as a result of charging. And then we figured, like, okay, if at some point we have fewer chargers than the number of buses at the station, it might be smarter to let the bus charge that has the lowest state of charge. And that is basically an idea behind the second strategy that we had in mind. So if there is a bus that is currently using the charger that is already at 80%, another bus comes in that only has 40% battery left, then you are actually allowed to swap the 2 buses so that the bus with a lower state of charge would actually get the charger. This is, of course, only relevant when the number of chargers is less than the number of buses that is simultaneously at the station. Okay, maybe to give an overview, this may be also a good moment to ask whether everything is clear here. So what we do have is we have 2 common sense strategies that we just evaluate. So we evaluate the impact of those. And we have 2 formulations that give us an optimized strategy, the DTO and the DEO, that we optimize and that we then also evaluate. Is this setup clear to everyone? Any questions on the strategies?
So it looks like it's pretty good, but I did want to ask just a little bit. So when you did the discrete event version where you were constraining decisions to when buses were arriving or leaving, you could also inject other times into that way of doing things, right?
Yeah, certainly. So indeed, if for example, if you know already that you have a very long time window somewhere in your schedule, which you potentially would like to cut in to, you could easily add some events. Of course, the more you add, the closer the computation time would be towards the DTO, but that's definitely possible. There is actually for other applications some work where they do that some sort of in a smart way, that you basically, based on the result of your optimization, already get a prediction of which events you would need to add to the model. But that we did not do. But there is different ways of adding events in order to actually get closer to the DTO optimal solution, so to say.
Oh, I see. So some sort of dual variable thing, or?
Yeah, exactly. That goes in that direction. We did not go that path, partly because we actually do like the discrete event, these events of buses arriving and departing, because these are actually very good moments to start charging, both practically as well as you would expect a lot of the optimal solutions actually also to use those slots anyway.
Okay.
So we actually like the constraint, even though it's not a hard constraint in the model.
Gotcha. Okay, thanks.
Okay. If there are no further questions, I will just continue. So we applied this to this northern network. So as you see, it's a bit more spread out over the region. So there's not a lot of overlapping stations, which is also the reason that we need many different stations with chargers. And it's really the spread out network over mainly the northern part of the city. Two of the lines actually also cross the river, but most of it is in the northern end of the city. We have a network of 57 buses. At first, actually, 10 of them will still be operated by diesel buses. So actually, we have 47 buses because the diesel buses we don't really need to take into account for this charging scheduling. So we basically have 47 buses. The buses that they actually purchased in the end had a battery of 240 kilowatt hours, and we had 15 chargers spread out over 6 different terminal stations. And then we have slow chargers in the garage for overnight charging. So these are really only used at the end of the day. The bus connects to a charger and basically spends most of the night charging so that it is full the next day. So this is just to get an idea of how this network looks. I will show 2 types of results. So first I will compare the 2 formulations that we had, and then I will also show like what this does for the for actually the charging pattern and how it compares to this common sense policies. So for this we have 32 different instances. Some of them on the larger network, so the full network that I just shown, and some of them on a smaller, basically a subset of the network to see how it would perform on small scale instances. And then we have different configurations, basically ranging from different numbers of chargers, different requirements for the state of charge, and some other practical parameters that we can change. And we run it for 900 seconds and or till it stops with an optimality gap of less than 1%, just using the CPLEX solver. And we just wanted to see how these 2 formulations would perform in this setup. And what we did expect was that the DEO is faster than the DTO, but it's actually much, much, much faster. So the DTO for the even if you have only 1 line, so 9 buses, it would use half of the maximum time that we allowed, whereas the DEO basically instantly gave a solution. And then for the larger full network, we saw that the discrete time formulation always required the full time. It still gave reasonable good solutions, but at least it could never give a guarantee within 0.01% of the optimality. And again, the discrete event optimization was done in like 21 seconds. So quite a big difference in computation speed. I think it was a bit more than we expected, but I think that's mainly due to the fact that the number of events is really reduced a lot by the policy that we used. Okay, but then of course, what would be the impact on the actual charging cost, on the actual objective? And then we saw that the DTO did find, or at least for 18 of the instances, actually find a better solution, but the difference is really, really, really small. So indeed, you do benefit a bit from this opportunity to basically change the charging bus at a time at which no bus arrives or departs from the station. But yeah, the highest gap that we have seen was 0.23%. So for us, that was like at least an indication that we have the most important events are in the discrete event optimization already. For 4 instances, we actually found that the DEO was actually finding a slightly better solution. So this is caused by the fact that some buses were charging for 4.5 minutes, and that would give like a slight edge compared to 5 minutes or 4 minutes. So that's where this gap comes from, but that is even smaller. But more importantly, this DTO was not even able to find solutions for some of the instances. So there were a few instances for which the DTO, after this 900 seconds, did not find a feasible solution. So we did find out, like, okay, given that the difference is really, really small and objective, the DEO is much faster and more practical. We prefer to use the DEO from now on. So this DTO, even though, yeah, could be slightly better, we still would prefer the DEO for future calculations. Okay, so now that we have done that, so we would like to compare to the solution that we would get to like this common sense strategy. So these are the strategies that first in, first serve, or lowest state of charge, highest priority. So these are the two that we have. And for this, we basically use most of the same setups. And yeah, so here are just some parameters, but I think these are quite standard. And then what we see is this is the resulting charging pattern. So in gray, you actually see the price signal that we use. So that is the energy prices over the different times of the day. And in the darker blue, you see the fast charging during the day. In the picture above, you see for the optimized schedule. And in the picture below, you see it for the first in, first serve charging schedule. And what we see is that there's approximately a 16% reduction in charging cost. Some of that can be attributed to choosing a smarter time to do the overnight charging. As you see, like the lighter blue line, you see that this charge that is charging in the garage, that could be done smarter in the first in, first serve. But also during the day, you see, for example, at 9 a.m., you see that there is quite a bit of charging in the first in, first serve solution, whereas the energy prices are highest at that time. And the optimized schedule is much more able to avoid charging at these times with peak demand. So you really see that the price signal that we put in the objective, you see it back in the charging pattern that you get as a result. Of course, the fact that you don't use all the charging, because first in, first serve basically uses all the charging slots, this of course has an impact on the state of charge of the buses. So it comes at a price. And this is the lowest state of charge of the different buses that we have. So we have 47 buses. And the lighter blue shows the minimum state of charge of this bus according to first in, first serve. And the other one is according to optimal. And what you can clearly see is that we had a constraint that the minimum state of charge should be higher than 40%. So the optimized schedule really tries to avoid fast charging if it's not necessary to make it to the end of the day. And you see that the first in, first serve basically has a lot of unnecessary charging during the day, because it's really not necessary to maintain a state of charge of 75%, for example, for some of the buses. So that you clearly see that there's just too much charging and it's not necessary to use all the time slots. Okay. And then we were thinking like, okay, maybe it's not too realistic to assume that we always have enough chargers. So that's basically what we assumed up to now. So what if we reduce the number of chargers to see that we actually have to make a choice which bus gets the charger. And for that, we basically reduce a few that we use less. So the chargers that we don't really use a lot, we remove them from the system. And instead of 17 chargers, we now have 8 or even only 6 chargers in the system. And then you actually see that first in, first serve might actually lead to more infeasibilities than the optimal schedule. Because first in, first serve never makes the right choice between different buses in assigning charging slots. It could be that a bus that is at a critically low state of charge comes at a charger and cannot charge because another one is using it at the time. And that you see that for first in, first serve, we actually have 6 buses that have a state of charge lower than the required 40%, whereas the optimal schedule here actually, with a bit of tweaking of the model, was able to get only one infeasible bus, so one bus with a state of charge that does not satisfy the requirements. So it's not only that first in, first serve might be more expensive, but it could actually also be necessary to do something smarter just from a perspective of feasibility. Okay, some conclusions for this part. So what we have is that it's much better to have this event-based formulation, and that we can actually benefit quite a bit from doing it in a smarter way than just using any of these common sense strategies. So it pays off to really optimize for these charging schedules. Okay. One, say, big elephant in the room that I did not really address yet is uncertainty. So for now, I just assume that we know the driving times of all the buses. There are never any delays. We know the energy consumption of the buses. And all of this, of course, is not the case. So what happens if you actually add uncertainty to this problem? So what we have had so far is we had a simulator that evaluate some greedy strategies and an optimized strategy. And now we add some stochasticity. So we add some delays, and we also add uncertainty in the energy consumption. So it can be that a bus takes a bit more energy or a bit less, depending on the weather, for example. And what we do now is that we quickly realize that probably our offline formulation would not be sufficient. So what we do is during the day, we re-optimize the schedule with the same formulation and update the charging schedule depending on the realizations of trip delays and energy consumption. And this would basically give us an online version of our formulation. Okay, there are a few technicalities because of the uncertainty, it could actually be that a bus arrives at the station and it's already below the minimum state of charge, which is a hard constraint in the model. So we actually have to think about how to deal with this infeasibility. So if a bus comes in with only 20% of battery, then we will not be able to find a charging schedule that makes sure that we have at least 40% at the end at all points. So what we do, we have some sort of procedure of making sure that we add as much energy as possible, as quickly as possible to the bus that currently violates the constraints that we have. So that's more or less the idea about this procedure. Okay, and then there was one final thought. So we did a lot of calculations with this online formulation, and then we figured out that it would require a lot of communication between basically some sort of control center that would perform the optimization and the bus drivers that in the end need to decide whether or not to charge the buses. And the operator clearly made very clear that that is not something that they are very keen on. They would rather give the driver some instructions beforehand so that they know when and where to charge, and there is no like real-time communication. So then we came up with some sort of heuristic, and that is what we call the dynamic threshold-based policy. So what we do is, based on this offline model, we come up with a threshold card that basically for each bus tells them, like, at this station, at that time, you should have so much energy left in your battery. And if you have less, then you use the charger. And if you have more, you don't use the charger. This is kind of a way of implementing some sort of adaptation based on the realizations, right? Because the bus driver can, in his bus, actually see what the current state of charge is. And then based on that, he can decide whether or not to use the charger at a given station. So this is basically an heuristic way of still having some online control. And this gives us a total of 5 policies. So the 2 greedy heuristics that we had before, the 2 optimized, so the online and the offline, and then the one that hopefully performs somewhere in the middle, which we call the DTB, the dynamic threshold-based policy. So again, we have similar parameters. We add some delays. We also have some uncertainty about the energy consumption. And then we compare the different policies. And what we see is that if we have enough chargers, so that's in this case, we have more chargers than we will ever need at any station. You can see, of course, first in, first serve, and lowest state, highest priority will always do best, right? They take any opportunity to charge. They always find an opportunity, so there will never be any infeasibilities. But you also see that they have the highest grid load. They have highest minimum state of charge. They have the highest number of charging events. So that is not really a solution that would be preferred. You could see that the online would still have, at least sometimes, have a bus that has a problem. So there is a bit of infeasibility still left. So apparently it's not fully possible to capture all uncertainty and avoid any infeasibilities. But you do see that you need much less energy during the day, so much less charging. So it could be that maybe they plan to have like 1 or 2 backup buses that you could pull out of the garage in case to capture these infeasibilities. But at least it's good to see that the DTB, so the one that dynamically implements this offline schedule, is actually able to avoid these infeasibilities. So that would be like a nice middle ground here. But then let's look at the case where we reduce the number of charges. So if there is actually a bit of competition between buses for the number of chargers, then we see that actually first in, first serve is not such a good solution anymore. Because apparently quite often a bus comes at a station where another bus is charging. It does not have a charger, and as a result, it will later in the day have an infeasibility. So this clearly shows that at least some sort of charging schedule optimization is important to get feasibilities. And again, the DTB is actually quite well able to reduce this number of infeasibilities while not getting too much of the grid load back in return. So it gives a nice compromise between like a fully optimized kind of schedule and like the ease of implementation from just using like this threshold cards. Okay. Yeah, I will take a few more minutes to tell a bit about renewable energy. That's the final topic that I had. It's only a few slides. So I will spend a couple of minutes to talk about that, because I also really like this part. And this is really about the southern part of the network. So here we, instead of having like all these charging facilities spread out over the city, we have really one central station where all the buses come to charge. And it actually is a quite, there's a big event hall there with a very big roof. And they are considering actually having a big solar park there. And the idea was to connect this solar park directly to the charging infrastructure of this bus network. So the question is then, how well is the renewable energy generation from the solar park aligned with the charging of the buses? And can we actually do that? Can we actually align those two? So that is the question that we had is, what is the value of installing the solar park with respect to reducing this impact on the grid, so that you don't charge from the grid, but that you charge from this solar park? And second, can we maybe improve even further if we maybe have some sort of energy storage system? So we have a big battery at the station, so that if at some point we cannot really use the renewable energy directly, maybe we can store it and use it later for charging. Okay, for this we use the Southern network. We have some data about solar power generation from a city that is quite close. It's not even in the Netherlands, but it's only 60 miles away. So we assume that the power, like the output of these solar panels, would be somewhat similar to the city that is only 60 miles away in Belgium. And then we use that to basically evaluate the impact on our charging. Okay, so we simulate for a full year, and what we see here is the line that you see is the actual renewable energy generation that we can expect for each of the different months. So clearly that is much higher in summer when there is much more sunshine, and much lower in winter. And what you see is the total energy that is consumed is without using any of the renewable energy. Then the second column gives, if we subtract everything that can be used directly from the renewable energy, so we don't need to take that from the grid, but would then be the load on the grid. And finally, we have the one if we also have this energy storage system. So we have the opportunity to store a bit of the renewable energy to use it later during the day. And that's also what the second graph is looking at. Really, what is the benefit of having this energy storage in this system? And for me, the nice takeaway, I think this is for me a very nice insight, is that the benefit of the energy storage system, so that is this line that you see in the graph on the right, is actually higher in spring and in autumn than it is in summer and winter. So what we see here is that the benefit of the battery is highest when the renewable energy generation is not too high and also not too low. And the reasoning here is that in the summer, there is so much renewable energy generated that basically at the beginning of the day, you charge the battery and you never get the opportunity to discharge the battery because you always have enough renewable energy to charge your buses. So basically you charge your battery and you use it when the sun is down, you use it to charge your battery, or you charge your buses, but that's it. Whereas in spring and autumn, you actually get the opportunity to first charge your battery, then discharge it to charge some of the buses, and then again charge it. So you can actually use more than one cycle of the battery. And I think that for me was quite interesting, that you don't get the best results either in summer or winter, but actually in this time in between where you actually have barely enough renewable energy, where you actually can use it more efficiently if you have the opportunity to store it. So that I think is quite nice about this result. That's all that I had. So maybe to wrap up, I think it was quite clear for us early on in the project that it requires a complete restructuring if you electrify your network. It's definitely gives you benefits if you do optimization and apply that to the charging schedules. There is at least, you need some sort of online approach to deal with the uncertainty. So either have like this dynamic threshold card or have a full online optimization. You need to do something to deal with this uncertainty. And I think it's also quite nice to see that renewable energy, at least if you have busy stations, you can actually directly use it for your for charging these buses, and you don't really need the battery, but the battery is especially useful maybe if there are not too many buses at the same time. Like if you have a station where only half of the time one of the buses is charging, yeah, that's a time where you probably need a battery to store it. But if you have this central station, then probably this energy storage system doesn't bring you a lot. It might still be worthwhile, but don't expect like miracles from such a battery at a very busy station. And that's all I had. So here's a picture of one of the buses that actually drives in the city now. So it's fully electric. And here you also see the charging infrastructure that I have been talking about. So it is overhead charging where the bus is parked under the charger. So if there are any questions, I'm more than happy to take them. And
okay, well, let's actually first thank Pieter sort of virtually. Maybe I'll do the clapping and just leave it at that. But people, you know, it never works to unmute. So thank you very much, Pieter. This is really cool. Looks like there is a question from Oktay.
Hi there. Very nice talk. Very nice work. Actually, it's also good to see integer programming at work, solving, you know, world problems. One thing I didn't exactly get is around slide 32. I think you showed us these two tables. In the first one, I think I saw that the first in, first served around this one. Yes. So first in, first served doesn't have any infeasibilities, but can you tell me what it does in the last chart here?
Yeah, so the last chart here gives like the lowest state of charge of any of the, I think it's actually the average minimum state of charge. So if you take the minimum state of charge of all the buses and average that over all the buses, then this is what you would get. And basically what you see here is that the first in, first serve basically charge whenever possible. So it keeps, it keeps the state of charge really high, basically, for all the buses. And that's what you see in this graph.
Oh, yes. Okay, very good. Thank you. That answers my question.
Okay, good.
So feel free to raise your hand or just jump in here. But I have actually a bunch of questions for you, Pieter. So I was curious, based on what you've understood here, these are purely electric buses, eh? They're not hybrid?
These are purely electric, yeah.
Okay. You know, I'm guessing just based on what you've been saying that Ithaca would never be able to manage pure electric buses just because of the hills and, you know, the winter and so forth.
It will certainly be much more complicated, both because of the weather that you get and the hills, that's for sure. It's, at least with the current technology, I think it would be really, really hard. Like probably every time you come up at the end of the hill, you need to charge. And so, no, it will be much more like the Netherlands is really flat, and the highest mountain that we have is the bridge over the river, basically, in this city. So yeah, that doesn't play a role here for sure, but yeah.
Yeah, so then fair enough, you know, I think that makes a lot of sense. So what about sort of more broadly? So as you've said, Rotterdam is very flat. Do you think that the right solution for public transit is a hybrid model as opposed to all electric, or do you think that all electric would be feasible more broadly?
Yeah, so it depends a bit on what goes on with technology, right? If you see like the difference between the buses that they were considering when we started this project and the buses that they ended up buying, and then like the second tranche of buses that comes in, and you see the differences in capacity, it goes really quickly. So I can imagine that Ithaca just has to wait a bit longer, and that it at some point still becomes feasible. I think. So I think that would definitely be my expectations, that at some point it will also for Ithaca become feasible. And it's not only about the geographical, it's also about how big are your lines, right? So the cities in the Netherlands are relatively small, so also the trips are not too long. So for example, we don't do any charging here when there are passengers in the bus. So passengers basically don't notice that you have an electric bus, except that it's a bit more quiet, and that would also not be the case for any city. So you have cities where they do very like minor charging events at every bus stop, right? Where you basically you park the bus, people go in and out, and maybe you charge for 1 minute and continue. And that really depends on the type of system that you're operating, whether that would be a better solution than having like slightly longer charging moments at terminal stations.
Gotcha. Okay.
Yeah, somewhat following up on the same thing. So at the beginning, you mentioned that one possibility is to, you know, have batteries and charge them. Another possibility is actually to swap the batteries in the bus. From a practical point of view or technologically, how hard is it to do this swapping? There must be a reason why, you know,
Yeah, so I think the systems that actually operate this kind of battery swapping system, they do that. They have basically machines to do that, so that goes automatically, but it's quite investment heavy. So you need like these machines to actually swap the battery. And what I've heard is that that is quite a bit more of an investment than just having a charger. And that basically results in that only happening at central locations. And even then, yeah. So at least for Rotterdam, so they did consider that option, but it turned out that that was for them not the best solution. But I know that there are systems that that operate like that. I think also that the firefighters were not too happy with basically a central location where a lot of batteries are stored. I think that was also like fire hazard was one of the reasons also to not be too happy with this kind of setup.
Gotcha. Oh, that's excellent. Actually, so I want to respect people's time. So I still actually have a few questions for you, Pieter. But maybe let's just thank you one more time, and then folks can head off, and those who want to stick around can. So thanks, Pieter.
Yeah, sure.